So here's a new linear system. And let's make it 2 by 2, let's make our lives easier here. And this time, let's make it, I don't know, 3x minus 4y is equal to, let's see, what's a good example? How about 3x minus 4y is equal to 2, and then x plus 2y is equal to 4. So here's a 2 by 2 system. And typically, when we solve a 2 by 2 system like this, we think about the rows, we think about the equations, and we put all the focus there. And we sort of read all these equations from left to right. In order to really unlock the keys to the kingdom in linear algebra, though, what we want to do is to take that focus that we have that goes from left to right and just turn it on its head. And to, instead of looking at these equations horizontally, let's look at them vertically. In other words, instead of putting the focus on the rows of a matrix, let's put them on the columns. And when we put the focus on the columns, what we're really doing is we're putting the focus on the variables. So kind of boxing these together like this. So here's our change in perspective that we're going to read from top to bottom instead of from left to right. And so what that permits us to do, put a 1 in front of that x there, is now to, from each of these blue boxes, factor out stuff that they have in common. So for instance, the first blue box here has an x in both of the factors. So I'll put an x that I factor out of that first column. Likewise, from the second blue box here, I'm going to take out a y. And then I'll have an equal sign. And then what remains in those blue boxes are just numbers. In the case of the box with the x in it, those numbers are 3 and 1. In the case of the box with the y's in it, it's negative 4 and 2. And then my last box already had just numbers in it, 2 and 4. And then I still have that plus that glued together those first two. But now I have a different way of looking at this system of equations. Whereas before I kind of had two separate equations that we were treating separately, now I kind of only have one equation. It's just that some of the entities in this equation happen to have multiple entries in them. So we package that 3 and that 1 on the x's into a single object. We package the negative 4 and 2 attached to the y into a single object, and the 2 and the 4 on the right-hand side into a single object. And in doing so, we create what we now call a vector equation. And that's the subject of this section. And this new vector equation is completely equivalent to our original system of two linear equations. And in the beginning, this looks just sort of like fatuous nonsense. Like, why would we do this? But this is the perspective that, as I say, is going to change the way that we look at linear algebra. It's going to change the way we think about the entire business that we're transacting here. Because what this allows us to do is to take the vectors, these things which are written in blue here, these columns, if you will, and we're going to think of them as being the stars of the stage here, instead of the equations. So 3, 1, this vector which is attached to x here. We're going to think of representing 3, 1 in my Cartesian coordinate system over here. 3, 1. We're going to call this vector something. Let's call it v. And whenever I write a vector as a single object, often I'll put a little arrow over it. If you're reading this in lay or in a textbook or in a quiz or wherever else it's written, sometimes in typewriting it's written just by making that letter bold-faced. So if you're reading it in the book, it's usually written with a bold face. If you're reading it on a chalkboard or a whiteboard or whatever I'm writing on these days, I'll usually put a little arrow over it. Sometimes in physics, they'll put an underline underneath it. I don't know. There's a lot of different conventions for denoting a vector. But keeping the vector quantities like 3, 1 separate from the scalar quantities, the single numbers, like x, for instance, is important business. And if you've taken a course in vector calculus, you probably appreciate that better than most. So how I'm going to represent this graphically is in a couple different ways. I could go to the point 3, 1 in my Cartesian coordinate systems and just place a dot there. But more to the point, I'll represent this vector additionally by drawing a little arrow that connects that point to the origin. So this is usually graphically how we think about what a vector is, if that vector lives in the xy plane. So there's what v is going to look like for our purposes. And then likewise with the second vector, negative 4, 2. Make that a different color so that we can separate them. Negative 4, 2. If I call that vector w, then I could represent w on this coordinate system by just going to negative 4, 2 and placing a dot there at negative 4, 2, and then maybe connecting that to the origin also with an arrow. So now here's w. And then likewise, the vector 2, 4 on the right-hand side let's call that b. For now, I'm just kind of picking names for these things. 1, 2, 1, 2, 3, 4. So here's 2, 4 on this same coordinate system. B. So the question we're asking now, if we're asking to solve this now vector equation, which results from taking this system of two equations and sort of bundling them together into one, the question we're asking is now, how can we combine together some multiple of the vector 3, 1 and some other multiple, perhaps, of the vector negative 4, 2 in order to produce the vector 2, 4. So I'll just write that out in English here again. What multiple of 3, 1 added to what multiple of negative 4, 2 equals 2, 4. And so the business of vector equations really involves two operations of arithmetic. And the two operations that it involves are, first of all, multiple, right? Multiplication, taking a vector like 3, 1 and multiplying it by a scalar, a single number, for instance, x. Right?
So you basically try to find x and y?
Yes, exactly. The goal is still the same. Okay? Whether we're solving it as a vector equation or as a linear system of equations, the goal is still to find what is x and what is y. X is playing the role of this first multiple that we're talking about, and y is playing the role of the second multiple that we're talking about. So the goal is still to find x and y. But the arithmetic that we're doing to these vectors consists of that multiplication by a scalar quantity, and also the second operation that's in play here is addition. And it turns out, and this comment is merely to prepare the way for something that we're going to tackle in more abstract sense later on. But did want to point this out here before we got any further down this road, that it is precisely these two operations that define what it means to be a vector. That vectors are defined by their ability to be multiplied and added. By their addition and scalar multiplication. Not multiplication by one another. In other words, we're not going to multiply a vector by a vector, but multiplication of a vector by a scalar. And it is these two operations that are what make vectors vectors. So in this new formalism, we're asking, how do I multiply the vector 3, 1 by something, x, and multiply the vector negative 4, 2 by something else, y, and add those results to get the vector b? So we have this nice picture. Let's figure out how to use this picture to answer the question. And that's exactly what the app that is available on Moodle that I'll ask you to pull out your laptops and play around with for our remaining phase today. Helps you to visualize. Any questions on this before we shift the screen over to the app for a minute? So here's the app. And here, instead of x and y, I've actually replaced x and y with C1 and C2. Don't be fooled. It's just a slight change in terminology. So C1 is playing the role of our x, C2 is playing the role of our y. So as we go along, just keep that in the back of your head. It's just a different notation. So in this app, what we're going to be able to do is, first of all, set up our vectors, v1 and v2, which, again, when you see those, we just called them a minute ago, v and w. So the first thing we'll do is set up what v and w were. Okay. So v was the vector, oh gosh, I already didn't write it down. What was the first vector? 3, 1. Okay, so I'll use this little slider to set my first vector to be 3, 1. There we go. It's being stubborn here. Do this in the keyboard. So I'll set this vector. That's more like it. And then we'll adjust the second vector to be, what was it, negative 4, 2. So drag the little v2 slider until that second vector is negative 4, comma 2. There we go. So there's our first and second vectors. And then our target, the b vector, which I did actually call b the way we wanted to, was the right-hand side. Was it 2, 4?
Yeah.
All right, I remembered that one. Cool. 2, 4. There it is. Okay. So now what's the goal? The goal is to figure out how to multiply v1 by something, x, and multiply v2 by something, y, in order that their sum hit the green point on this. So now it's a bit of a game, right? We've got these sliders down at the bottom, which are the coefficients, c1 and c2. Again, that's our x and our y. And so now just by playing around with these, so choosing our coefficient for x to vary to whatever we want it to be, and choosing our coefficient y to vary to be whatever we want it to be. We just want to find a combination which makes it so that the sum, which is the purple vector on this diagram, lands us exactly at the green point. And if I adjust this carefully enough, there we go. Oh, come on. Let's get just a little more, actually. Oh, yeah, if you click the little plus button there, you get a little finer control on it if you need it. There we go. Now we're right at the green point. So what do you conclude from this picture? That if I'm trying to solve the system of equations x times 3, 1 plus y times negative 4, 2 is equal to 2, 4, and 2, 4 is this point right here, then what are the coefficients, what are the x and y that do that according to what you see here? 2 for x and 1 for y. I agree. So 2 times 3, 1 plus 1 times negative 4, 2 is equal to 2, 4. Again, where did that come from? It's just these coefficients down here in the app. It's also shown right here on the graph. You can see what twice the vector 3, 1 looks like right there, 2 times v1, and then 1 times the vector negative 4, 2 is right there. And their sum is this purple vector that happens to land exactly on the green point, b, that we wanted. And this is now a different graphical perspective on what it is like to solve a system of linear equations. It's really just we have this pair of vectors, v and w, or v1 and v2, and we're just trying to figure out how to multiply each one of them by a constant and add the results together to land on a point that we choose, which came from the right-hand side of our equation. So to use this app, just set up your vectors, v1 and v2, set up your right-hand side target, b, it's going to be the green point on this graph, and then go play around with the coefficient sliders until you find the combination that lands exactly on b. And through that process, you have solved this linear system of equations. You should check, if you have the energy and the time, that if we were to use the elementary row operations to solve our original system, 3x minus 4y equals 2, and what was it, x plus 2y equals 4, that using elementary row operations to solve this, we would also have arrived at the same solution. But again, this is a different perspective, and it's one that we're going to be able to do a lot with. In fact, very often what we're going to do with this perspective is actually the opposite. To take a question about vectors and to translate it into a linear system of equations. That's a very common thing we're going to do this semester. And because once we translate it into a question about a linear system of equations, then we know what to do with it. Just solve the linear system of equations and tell me about the nature of its solutions. So in this particular example, how many solutions did this system have? It had only one solution. If we row reduce this matrix far enough, its reduced row echelon form is an identity matrix. Right? So this had a unique solution, which means that there is only one way for me to set these coefficient sliders that will land me on the green point. But we're going to get a lot of mileage out of this app, because a lot depends on the vectors themselves, v1, v2, as well as on the target vector b, on whether or not it is possible to land on the green point, or if it is possible, how many different ways are there to land on the green point? That's the question of, do we have a consistent system? If not, then there's no way to hit the green point. And if we have a consistent system, is the solution unique? It's not if there are more than one way to land on that green point. So before you get working on this app for today, let's take another look at the dreaded terminology that's in play here that Lei and I love so much. Any questions about the business of doing this before we do that? There's just a couple definitions I want to get out there. And the first is, a slide ago we were talking about the operations that go into making a vector equation. And those operations were twofold. There was scalar multiplication, in other words, this product of C1 times V1 and C2 times V2. And there was also addition. Right, this plus that's right there in the middle. Those are the two operations, again, that make vectors look and taste and quack like vectors do. Right? They're the defining operations of what make vectors vectors. Taken together, that combination of operations is called a linear combination. So scalar multiplication and addition makes what we call linear combination. So if I say, find a linear combination of some set of vectors that does some particular thing, what I really mean is multiply those vectors by some scalars and add the results together. That's what a linear combination is. It's just any combination we make of scalar multiplication of vectors and addition.
So when you add them together, or just a combination of them?
Any combination of doing those operations. So I can choose just to add, I could choose just to multiply by scalars, or I could do a little of both. And any one of those is a linear combination. So that's the first thing. And the second bit of definition, and this is a big one. Linear combination is big, but this one is particularly far-reaching definition, is the span. The span of a set of vectors. And let's just take two vectors for the moment. If I have a vector v1 and a vector v2, then what do I mean by the span of these two vectors? What I mean is, first of all, the span of two vectors is a set. So it's not a vector, it's not an equation, it's not a number, but it's a set. And it's the set of all linear combinations of v1 and v2. So just to get a feel for this, of v1 and v2. Let me ask you for a hypothesis. If v1 and v2 are the vectors in this diagram here, 3, 1 and negative 4, 2, the ones we were working with before, what do you think the span of those two vectors looks like? Another way to think of it is, going back to the app for a second, the span is the set of every possible purple vector that I could get by taking every possible linear combination of these vectors. So any point in the xy plane that I can land in with one of these purple vectors belongs to the span of v1 and v2. So maybe I can ask this question in a little bit more leading fashion. Is there any place in the xy plane that I cannot land with one of these purple vectors? In other words, is there any place that I could put this little green target that I would not be able to hit with a purple vector? I might have to do a little bit of working to make it happen. Getting closer. Whoops. But is there anywhere I can't go? Yeah, I could tweak this until Saturday and get closer and closer, whatever. Is there anywhere I can't go? It doesn't look like it. So, but we don't yet have the tool work to prove that, or maybe we do. What we want to be able to build into, both today and tomorrow, is understanding how this picture relates to the nature of solutions of a linear system, the question of consistency and the question of uniqueness. Is there a solution? And if there is a solution, how many solutions are there? If there is some place that I cannot reach by a linear combination of these two vectors, then there is some linear system of equations with those vectors as the columns that's inconsistent. And if there is no such, then that means that whatever is on the right-hand side must always give me a consistent system. These are the kinds of questions we're going to ask more and more. But I wanted to get it out there for now, so that when it comes back to us, we'll remember what it was all about. For now, let's just hang on to, first of all, linear combinations, being this operational process of multiplying vectors by scalars and adding the results, and that the span of a set of vectors is everything that we can make from linear combinations of those vectors. And so your prediction, if Catherine is trying to convince us that we can get anywhere by a linear combination of these two vectors, linear combo of 3, 1 and negative 4, 2. This means that the span of those two vectors is what? It's the set of everywhere that we can get. But if we can get everywhere, what is that set? Well, the set is every point in the xy plane. So we might just write it as the whole xy plane. If we just want to write it in words. And if we wanted to write it in notation, we might call it something like R2, the real two-dimensional plane, the set of all points x comma y, where x and y are real numbers. So that's just a taste of where we're going to push this concept into.